Today we're going to be talking about related rates. This is how the rate of a reaction or the rate of formation of one reaction component relates to the rate of formation of a different reaction component, and how each of those might relate to the reaction rate or rate of reaction. So we can monitor this reaction as a function of any of these reaction component concentrations, but we have to relate them back to each other. We have to keep in mind that they have different rates, right? So the rate of disappearance of N2O5 will be twice the rate of appearance of oxygen, because when 2 molecules of N2O5 are lost, only 1 molecule of oxygen is formed. So oxygen should form at only half the rate that N2O5 is lost. Also, NO2 will form at 4 times the rate that oxygen forms because of the stoichiometry. I have a little cartoon. I've simplified the molecules a little bit to make them easier to see. If we could keep these in separate flasks, which of course we can't, but let's pretend we can, we'll start with just our reactant. And as the reaction proceeds, what you should notice is that NO2, the blue spheres, are at a much faster rate than the green spheres. And of course, the disappearance of spheres is than the rate of the other two. So depending on the one monitoring, we have to be able to relate that back so that if we all came in the room together to talk about the rate of this reaction, we would be comparing apples to apples. I can't talk about the rate of formation of NO2 and somebody else be talking about the rate of formation of oxygen when we have to make sure we understand that they're not the same. We have to relate them back to each other, and we have to what's called normalize our discussion. So we're going to talk about related rates and a related rates expression. The first thing we're going to start with is our generic reaction. We're going to be using this reaction a lot in the future. Lowercase letters are stoichiometric coefficients, so those are going to be numbers. And the uppercase letters are going to be reaction components, so those are going to be molecules, compounds, elements, whatever is in the reaction. A and B are reactants, C and D are products. Our related rates expression, we're going to write next based on this syntax, with lowercase letters being stoichiometric coefficients and uppercase letters being reaction components. Rate of reaction is whenever you see that term in a table or someone asks you about the rate of reaction, that's what that means. The stoichiometric coefficients are the lowercase letters, and so you can see the -1 over lowercase a. Those lowercase letters are all the stoichiometric coefficients as they appear in the reaction, in the balanced reaction. And remember that the brackets mean molarity, and so those are change in molarity of A over change in time, change in molarity of B over change in time. These negative signs for the reactants are negative because the rate of reaction is always positive. But the change in reactant concentration over change in time is a negative number because reactants decrease over time. So to make them positive, we put a negative sign in front of that. Okay, so let's practice one with a real reaction, like our favorite reaction here. We're going to write the related rates expression for this reaction. So here we are. The rate of reaction on the left. Don't forget to write rate of reaction, because I might ask you a question. I might say, calculate the rate of reaction, and you're going to say, I don't know what you're talking about, and you'll forget that left side of the equation. Rate of reaction equals. So now our expression with actual numbers in it is -1 over 3. That's because the stoichiometric coefficient in front of hydrogen was a 3. And then delta H2 over delta T, that's the change in hydrogen concentration over time. Or you would also call it the rate of change of hydrogen concentration. And then negative delta N2 over delta T, there's no fraction there because there's no stoichiometric coefficient, it's a 1. And then positive 1/2 change in concentration of ammonia over change in time. So those 3's go together, right? There's a 1 in front of the N2, which is why there's not a fraction there. And then the 2 in front of ammonia becomes a 1/2. And that last one is positive because it's a product. And the first two are negative because they are reactants. We're going to do this practice problem to make sure everybody knows how to do related rates problem. Now this is combined with just a calculation of an average rate. So we're going to start with that. So you perform the following reaction in the lab, collected data for a single experiment. This is the decomposition of dinitrogen monoxide into 2 molecules of N2 and 1 molecule of O2. We have in our data table time with minute intervals, 0, 60, 90, 120, and 180 minutes. And then the concentration of N2O, which is our reactant concentration, as a function of each of those time points. So part A, we're going to calculate the average rate of change of N2O for the 60 to 90 minute time interval. So one thing that you should probably get used to is the terminology. Okay, so average rate of change. Remember, it's an average rate, so we're just using time intervals. And it's asking for N2O, which is what the data table is describing. And it's the 60 to 90 minute time interval, so those are the two data points we care about. So average rate of change really just means delta N2O over delta T. Okay, so we're really just doing the change in N2O concentration in the numerator and the change in time in the denominator. So 0.204 is our final concentration, and 0.218 is the initial concentration. And then the denominator is 90 minus 60, the final time minus the initial time for that interval. And you end up getting a negative number in the numerator and a positive number in the denominator. So our final answer will be negative. This is telling us here that our sig figs are ambiguous. I did a pretty terrible job of giving you better sig figs. So what I'm trying to tell you up here with these little dots that didn't come out very well is that I'm putting a dot there. I'm saying that we're going to assume that these numbers are accurate to the nearest minute. So this is really 0 point minutes and 60 point minutes. So they're accurate to the ones place. So we're going to make that assumption rather than worrying about the ambiguity of this terrible question that I gave you. And now you see that the numerator is negative 0.014 molar divided by 30 seconds. And that is going to give us negative 4.66. And that line over the 6 means it goes on and on and on forever. The 6 is continuous. So it's 4.6666666666 until infinity times 10 to the minus 4 molar per second. And that's going to round to two significant figures because the 30 in the denominator and because the numerator only has 2. So the numerator has 2.014 and the denominator has 2, 30. And so your answer should be rounded to negative 4.7 times 10 to the minus 4 molar per second. So we're going to move on to part B. Calculate the average rate of change of oxygen for the 120 to 180 minute time interval. Now, this one's a little different. This is a related rates problem because it's asking for rate of change of oxygen, but you're not given data for oxygen, you're given data for N2O. So the first thing you have to do is calculate the change in concentration of N2O and then relate it back to the change in concentration for oxygen. So we'll start with N2O. This is really just a repeat of the one we just did, except for a different time interval. And you can see that you get negative 0.024 molar per 60 seconds, which is negative 0.00040 molar per second. Now we have to relate that back. That's not the answer. We're going to write our related rates expression, which is shown here. Rate of reaction equals negative 1/2 delta N2O over delta T. That's what we just calculated actually, is the delta N2O over delta T, equals 1/2 delta N2 over delta T. We don't really care about that. What we care about is that last piece, the delta oxygen over delta T. That's what we're asked for. 2. That 1/2 is because of the 2. And we're going to combine these two, put them together in an expression. We're going to plug in negative 0.00040 molar per second for that delta N2O over delta T. I'm going to erase some of the stuff up here so that we can make some room. I didn't leave myself enough room. I'm going to rewrite this expression. Negative 1/2, and I plugged in the number instead, right? That what we calculated in that first part. And then I solve for delta O2 over delta T, and I get this number, 0.00020 molar per second. It's now positive because oxygen is a product, so it should form at a rate at a positive rate. Change in concentration should be positive. Now we're going to erase that. Here I'm trying to tell you that final answer. Now let's do part C. Calculate the average rate of reaction for the 0 to 60 minute time interval. Let's do that first and then we'll answer the last part. So rate of reaction. Remember our related rates expression. All we know is the change in concentration of N2O. So we're going to calculate that first for 0 to 60 minutes. Oop, I wrote seconds, it should be minutes, and it's negative 5.3. That line over the 3 means it goes on and on and on. 3 times 10 to the minus 4 molar per second. And then our related rates expression is here, and you can see that rate of reaction, we're just going to plug that number in for delta N2O over delta T. So I just plugged this number in for this expression. That's what we calculated, right? You can see that here. Plug it in, so it's inside the parentheses. The negative 1/2 is still there. And we calculate 2.7 times 10 to the minus 4 molar per second. And that's that answer. Now we need to finish this last part of the question. Oh, we're doing sig figs now. So our sig figs are accurate to 3 digits after the decimal. That was why that was like that. Let me back up. There we go. Let me back up again. I can't seem to get it all done. Okay, so our significant figures here, it's showing you that these are accurate to the tenths, hundredths, thousandths place, right? 3 digits after the decimal. That's true here too. That actually reduces this number to only having 2 sig figs now. And the 60 has only 2 as well. So our final answer only has 2. Now we're going to answer this last part of the question. If you repeated this calculation for all time intervals, would you expect the rates you get to increase, decrease, or remain constant? This is related to something we talked about before conceptually about instantaneous rates and why we use initial rates. And so if you remember, what we said is that initial rates at the beginning, it is always the maximum rate. It always decreases over time. So the initial rate is always the fastest one. That's one of the reasons we use it. Rates will always decrease over time. And so we would expect it to decrease if we repeated it because that's the first time interval. It will only go down.